Hello, and thanks for taking your time to watch our brief presentation on the SR 520 pontoon and floating bridge projects. We'll give you an overview of construction and an update on our next steps. Let's begin. Today, we are going to walk through 5 key topics. First, our goals for the SR 520 floating bridge and pontoon projects. Second, a look at the work we've done to date to build a new floating bridge. Third, we'll talk about some of the challenges we've faced in building the SR 520 bridge pontoons. Fourth, we'll talk about the repairs we have made and are making to bridge pontoons. And finally, we'll wrap up with our plan for future pontoon construction cycles. As we all know, the SR 520 floating bridge needs to be replaced. The existing bridge and structures are vulnerable to earthquakes and windstorms and could collapse in a catastrophic event. Also, the 4-lane structure needs to be expanded to accommodate projected population and employment increases on both sides of Lake Washington, while also providing new options for transit riders, bicyclists, and pedestrians. The new SR 520 floating bridge will be built to modern safety standards and will be able to withstand windstorms up to 89 miles per hour. We are excited about new inside transit and HOV lanes, wider, safer shoulders, and a bicycle and pedestrian path on the north side of the bridge. The new bridge's east channel will match the height of the I-90 bridge, meaning no middle drawspan and no more drawspan openings. To get there, we have a lot of work to do. We've constructed a pontoon casting facility in Aberdeen, Washington. We'll use this site to build a total of 33 pontoons through 6 different construction cycles. In the first cycle, we built 3 longitudinal pontoons, 2 supplemental pontoons, and 1 cross pontoon. We are also building 44 supplemental pontoons in Tacoma. These are the smaller pontoons that provide flotation for the long pontoons. In Kenmore, we're building a variety of bridge anchors, as well as precast deck panels that will form the new roadway. We'll assemble all of the components together to build the new floating bridge north of the existing one. As you can see, the pontoons are massive structures. The largest of them are 360 feet long and weigh 11,000 tons. They need to be large in order to support the new 6-lane 520 bridge, yet still small enough to fit through the Ballard locks in Seattle. These complex structures include a variety of components, like rebar throughout the pontoon form, interior precast panels and concrete walls poured around the bottom, top, and exterior, bolts to connect pontoons together, and ducts for the post-tensioning system. Now we're going to discuss some of the challenges we've faced. In May, we completed major construction on the first cycle of pontoons in Aberdeen. This is a pontoon prior to post-tensioning. A natural property of concrete is that it cracks, and we easily repaired the cracks we found at this stage. Later that month, we prepared the pontoons for post-tensioning. Post-tensioning is a standard practice in major construction projects when crews tighten metal strands within the concrete for additional strength. You can see the steel strands placed through the ducts on the ends of the pontoons. After we completed post-tensioning of the pontoons, we encountered 2 key issues. The first is cracking. After post-tensioning, we saw cracking in the end walls of 4 out of 6 pontoons built during the first construction cycle. Crews repaired these cracks with a standard combination of epoxy injections and crystalline waterproofing. The second issue is spalling. Spalling is when concrete chips or flakes away. We saw spalled concrete in Pontoon V, a longitudinal pontoon related to the design of the tensioning ducts, but more on this in a moment. We repaired the spalled areas by removing the concrete, adding rebar, and placing new concrete in the area. After we took this corrective action in Pontoon V, we made preemptive modifications in the other 2 longitudinal pontoons. When we finished post-tensioning those pontoons, we didn't see any spalling. We also made preemptive modifications in the cross pontoon, which held after lengthwise post-tensioning. However, we encountered spalling after post-tensioning across the middle of that pontoon. We made repairs, post-tensioned it again, and did not find any additional spalling. In June, WashDOT convened a panel of experts with expertise in civil engineering, floating bridge design, bridges and heavy structures, and pre-stressed concrete. These experts were directed to determine the causes of cracking and spalling, review the repairs made to the first cycle of pontoons, and make recommendations for the future pontoon construction cycles. They submitted a report in August and found that the placement and location of the post-tensioning ducts contributed to spalling. They also noted that the interior precast walls were attached directly to the end walls. This connection led to resistance during post-tensioning and contributed to end wall cracking. For the full details, you can read the entire report and WashShot's response on our website. By July, our repairs were complete and endorsed by the expert panel so that we could proceed with the pontoon float-out by flooding the basin. We then inspected for leaks in the pontoons during and after the basin was flooded. On July 30th, we floated out all 6 pontoons from the Aberdeen casting basin. They were then towed to the port of Grace Harbor for further inspection. July was a busy month for us, as we also floated out all 6 pontoons built in the Tacoma casting facility. There was minor cracking and moisture in these pontoons that was repaired, and we will continue to monitor them on Lake Washington. Before the pontoons could make their final trip to Seattle, we inspected them thoroughly in the port of Grace Harbor. We inspected each internal cell and the bottom of the pontoons using an underwater diver. You can view their videos on our website. After some repairs were made, we were ready to tow them from Aberdeen, around the Pacific Ocean, through the Puget Sound, and into Seattle. The first pontoon was towed through the Ballard Locks in Seattle on August 11, 2012. By the end of September, all 6 of the Cycle 1 pontoons were towed to either Lake Washington or Tacoma for additional outfitting. However, our pontoon work isn't done. If you've driven across the 520 bridge lately, you've seen how much is taking place. Crews started construction on a coffer dam to have a dry area to build new SR 520 bridge piers. They installed several anchors in Lake Washington to connect the new floating bridge to the lake bed. Crews are also beginning to join the pontoons together on the lake. You may have heard reports of moisture in the pontoons. This moisture can come from several possible factors, like water deliberately placed for temporary ballast, residual water from concrete curing, some plugs in the bolt sleeves may be missing or misaligned, hatch doors or other temporary maintenance access points may be open, or there could be cracks or gaps at construction joints that haven't yet been sealed. Our contractor is working on these issues and other needed repairs on Lake Washington, a better work environment than the saltwater and tidal currents in Grace Harbor. Again, our work isn't finished. The contractor has until 2015 to open the new bridge, and we are working to make sure it meets all contract requirements. WashDOT will not accept the pontoons until they meet the 75-year design life called for in the contract. Now that you know the whole story on the first cycle, let's talk about changes we're making for the future. First, we are going to implement recommendations made by the expert panel. In order to reduce spalling, we are changing the post-tensioning duct design. In the first cycle, we did not have enough rebar and concrete to contain the force of the pontoon tensioning. In the second cycle, the curve of the post-tensioning strand will be better contained under additional concrete. This will eliminate spalling in future cycles. Next, we are going to decouple the precast panels from the end walls. In the first cycle, the panels were attached directly to the end walls. During post-tensioning, this contributed to excess stress and cracking on the end wall. In the future, we will adjust our construction sequence by not pouring concrete between the panels and the end walls until post-tensioning is complete. This should relieve stress on the end walls and reduce cracking. We will also use shorter wall pours and improved thermal controls to reduce cracking throughout the pontoons. We've asked the panel to stay engaged with the project through the next 2 cycles of construction in Aberdeen. They will review the structural capacity of pontoons, assess the quality of pontoons already constructed, review methods to identify and repair cracks, and assess potential maintenance needs of the pontoons to ensure the long-term effectiveness of crack repairs. We appreciate your interest in the project and your patience as we move further into construction. We hope you have a better understanding of the work it takes to build the longest floating bridge in the world. WashDOT and its contractors are committed to building a safe, high-quality bridge that will serve the region for 75 years or more.